Okay, so thanks to Chenlei for the invitation to give this talk. Actually, I'm not going to be talking about this particular work, but I'm going to be talking about something very much related, and I'll try to motivate it from this previous work. So the title of my talk is actually quite generic, and there's many, many ways you could think of to speed up Monte Carlo methods. And so I'm first going to try to explain what I mean exactly by speeding up Monte Carlo methods and in which specific context I want to do this. So before I start, I should mention a few people that have worked with me on this, mostly Chris Oates, who used to be at Warwick and is now in Sydney, Mark Girolami, who's my supervisor, John, who's hiding at the back of the room, and then Dino, who you heard a talk from earlier, and also Mike and Tony. So the problem that I'm going to be considering is that of computing integrals. So I'm going to be considering this type of integral where f is going to assume to be nice. It's going to be defined on some subset of Rd, or maybe the whole of Rd. It's going to be square integral. And I'm going to have a density pi, which is also going to be fairly nice, let's say. So I want to compute those integrals with respect to this density. And in a lot of problems in statistics, you can't actually do this analytically. And so this is why Monte Carlo methods are so popular, because they allow you to approximate these sorts of integrals. So the general framework to approximate an integral is something called a quadrature rule. So this is exactly this. So what you would do is you would evaluate your function at a bunch of points, and then you would weight those somehow. And then the idea is that if you pick your points well and your weights well, then the right-hand side here will tend to approximate the left-hand side as the number of function evaluation increases. Okay, so just to review a few basic ways of doing this, maybe you can use standard Monte Carlo. That would be just, I'm going to sample my points from the density, and I'm going to weight them all equally. And that's really basic. Maybe if you're in a Bayesian context, well, you run into the trouble that you don't actually know the normalizing constant of pi. And in this case, what you might want to do is use a Markov chain with invariant distribution pi. And so you're going to run this chain and then evaluate your function on the history of the Markov chain. Then there's also many, many other ways that people do these kind of things in statistics, maybe Gaussian quadrature, importance sampling, QMC, SMC, blah, blah, blah. So my work in this area has really focused on two different, has had two different focuses. The first one is concerns the emerging field of probabilistic numerics, and the idea is that you're trying to quantify the uncertainty associated with the fact that you're using an approximate procedure. So here we're using Bayesian non-parametric models, like Judith mentioned previously, to try to get posterior distributions on the solutions of these integrals. And so I thought I should just mention this, but I'm not really actually going to be talking about this throughout the rest of this talk. The other, I'd say, focus of this work has been, well, how can I build a quadrature rule? So how can I pick those points and those weights so that I have a quadrature rule that approximates the true integral very quickly? And I'll make this a bit more precise below. So this is what I mean by Monte Carlo, and what I mean by very quickly is I want the root mean square error to be as low as possible for a fixed number of points. For a fixed number of points, n. So I really want to minimize this root mean squared error. And I'm going to study methods that kind of do this and study how they can reduce this error asymptotically. So why do I want to make this small? Well, of course, to have a much smaller error in your integrals, but there's actually some very important applications where you actually want to do this in cases where your number of function evaluations is very small. So if your function is very expensive, then you really want to minimize this root mean squared error. So one example, which I guess is really quite relevant at the minute with the problem of hurricanes in the US, concerns simulation of those hurricanes. So there's this Wall Street Journal article that came out a few weeks ago that explains how you can use Monte Carlo methods to kind of predict what's going to happen with hurricanes. So you might have a very complex model of the weather, and you might know where your hurricane is currently. So something you might want to do is simulate from this model to try to predict where it's going to be in 2 days, say. And that's going to be really important because maybe you want to send all of your emergency services to wherever this hurricane is going to be. So here, I guess my x's, my points, would be simulations from this on this computer of the hurricane, and I'm trying to maybe predict where the posterior expectation is. Where does this hurricane end up in 2 days? Another problem, which is really quite important, is, well, not important, but where reducing the error in Monte Carlo estimation is really quite important, is the rendering of images. So recently I attended this talk by some people from Pixar, and they were explaining how, well, essentially to do rendering of images, they need to compute loads of integrals at each of the pixels of this image. And so the better the integral is, the better the quality of the picture will be. Better the approximation of the integral is, the better the quality of the picture will be. So here, what they currently do is they use Monte Carlo methods, and they take about 60 hours per frame for a given cartoon. And obviously that costs them quite a lot of money, and so you really want something that's going to make the best use of your Monte Carlo simulations. Okay, so that's the context. So as I said, I want to minimize this root mean squared error, and so the way I can do this is by choosing a quadrature rule that will minimize this. And so what I can do is either improve my weights or improve my points. And so I want to study how this will be minimized, well, how this reduces asymptotically as n increases. So in the simplest case, if you take simple Monte Carlo or MCMC, this will reduce as n to the minus 1/2. And you can show this using some kind of central limit theorem. And this will be well, very good if you're in a very high dimensional problem, because you can notice that there's no mention of dimension in the rate, so that's pretty good. But for many of the problems that I mentioned previously, this is actually too slow, because it means that I'm going to need many runs of my Monte Carlo in order to reduce this error. And so what I want to do is try to somehow improve this rate. Okay, so something that people have done is called quasi-Monte Carlo, and this just consists of somehow spreading your points, so the x's, across your domain. So essentially to just really cover it quite well. And you can actually gain in terms of convergence in this case, and you get n to the minus 1 plus something very small. And that's already a lot faster than n to the minus 1/2, so you gain a 1/2 factor. And in the case of smooth functions, you can get n to the minus alpha over d plus something small, so alpha being how many derivatives the functions that you're trying to integrate have. And that's a lot nicer. So this is going to be, of course, if you have a very smooth function, which is not too high dimensional, then this will be much better than just standard Monte Carlo. The problem with this is that, well, to spread your points on the domain, you have to be on a fairly nice domain. And so this isn't going to work all the time. It's going to be restricted to certain types of domains. Something else that's quite problematic is, for example, in the Bayesian setup, where I don't know what the normalizing constant of my density is, then I can't actually use this. And so, well, I can't really do anything in the Bayesian context to actually speed up on this n to the minus 1/2. So the aim here is really going to be to improve on n to the minus 1/2 in the context of intractable density. Okay, so is there any questions up to now? No? Okay. So the way, so I'm going to try to find a method which can do this. So by finding a method, I'm just going to try to find some weights and some points which can do that. And the way I'm going to be motivating how to find this method is using something I've worked on for quite a while. It's called Bayesian quadrature or kernel quadrature. I guess you all know everything about Bayesian non-parametric models and kernel methods from the first two talks, so I don't have to explain too much about this. But essentially, the idea is if I want to integrate a function, which I can't integrate analytically, say this red curve, one way that I can do this is simply by using a non-parametric model, maybe doing kernel regression or Gaussian process regression, and start evaluating my function at some points and then interpolating with this non-parametric model. So of course, here the blue curve is my interpolant. So the more I evaluate the function, the closer I get to the red curve. And so then the intuition is that I could integrate my blue curve instead of the red one. And if the blue curve is close enough to the red curve, then the integral of the blue curve should be close enough to that of the red curve. So that's how the method works. So I'm assuming that I can integrate this blue curve analytically. So I'm going to choose the interpolant in a nice enough family of functions so that I can do that analytically. And then essentially, I'm replacing the problem of integration by that of regression. So here, my posterior mean of this Gaussian process takes this form, where K here is my kernel matrix. This is just a vector of evaluations. So it's just a weighted combination of function evaluations, and the weights depend on the kernel. And so if I integrate this interpolant, which is a blue curve, I just get, well, the integrated weights. And this is what I'm going to be calling the Bayesian quadrature estimator. I haven't really mentioned anything about why this is Bayesian or anything. That's not really going to be relevant for this talk, so I'm not really going to mention it. OK, so now we've now got a quadrature rule because we have a bunch of function evaluations and some weights. This is exactly in the same framework as earlier. Of course, here, this choice of kernel will be really important for the performance of the method. So as Judith explained in the previous talk, the kernel will really influence what kind of functions you get out, and therefore what kind of interpolants I can get. So if I choose a very rough kernel, then I'm going to get very rough functions. Here I've used a very smooth kernel, so I have nice and smooth curves. Essentially, this is a way for you to use some prior information you might have about your integrand to kind of improve on the performance. So if you choose your kernel well, then you'll get really good performance with this. I'm not saying choosing the kernel well is easy, and I'll come back to that. So this is just a small toy example to show you how much improvement you can actually get with this. So here I've picked my function to be sin x plus 1, and my density to be a normal 0, 1. I can integrate this analytically. The solution is 1. Therefore, I can actually compute my root mean squared error. Well, actually, this is the mean squared error. But, and I've used the Gaussian kernel like Dino was using with a fixed length scale. And so the blue dots here is how how a simple Monte Carlo estimate converges as n increases. And the green curve here is the case where I've reweighted these samples, these Monte Carlo samples, with my weights obtained here. So of course, it's a lot faster. And I should point out that this is in log scale. So the error decreases much, much faster. So here, if you can only evaluate your function, say, 100 times, then you get quite a significant speed up. And it's actually really worth using. OK. So just to summarize what I've said so far, well, one of the main advantages of this method is that you can be quite flexible in the kind of information that you're inputting into your integration rule. Although this may not be so easy, as both of the previous speakers mentioned. This method has pretty fast theoretical and empirical convergence rates. And this is some work that I did in this particular paper. However, on the more, well, there are also some quite big disadvantages. The first one is you have now a biased estimate of your integral. And then computing those weights is often quite a big challenge. So there's a few challenges. The first one is that because you need to invert this matrix, it can cost you up to order n cubed, where n is your number of data points. And that's actually, well, quite a lot more expensive than simply doing Monte Carlo, which would cost you of order n. So that's why I said this method is mainly going to be used in cases where your function is really expensive, and then it doesn't matter because you don't have that many function evaluations, so inverting this is just going to be trivial. This inversion can also be sometimes unstable. But really, the main problem that we have here is that we need to be able to compute integrals of the kernel. So what Dino earlier mentioned, which is called the kernel mean. And so this is OK for a few simple choices of distributions and kernels, but it's not going to be true. Well, you can't do that for a wide range of those. In particular, you can't do this in the context of posterior. Well, if you're considering the Bayesian setup and you have a posterior, then you don't know the normalizing constant. Therefore, you can't know this, and that's pretty problematic for the method. And so essentially, you can throw all of this away because you can't use it in this context. So I'm now going to briefly mention how you can solve some of these issues. The first issue that I mentioned was the fact that we had a biased estimate of the integral. And that's pretty problematic in some application. However, it's quite easy to remove this bias. And something that you can do is just you use what I call the control variate trick, where you actually just separate your data into two batches. And then you use an estimator where, with the first half, you compute your standard Bayesian quadrature estimator, which is just the integral of the posterior mean of the Gaussian process. And with the other half, you just compute a Monte Carlo estimate of the difference between the posterior mean and the actual, and the actual function. So here, the posterior mean is obtained with the first half of the data, and I'm computing the difference between the two on the other half of the data. And you can show that this is actually now unbiased. So simply by separating my data in two, I can get an unbiased estimator. OK, so that was maybe the more trivial of the two problems. As I mentioned, the biggest one is really how to compute those weights. So to speed up the inversion of this gram matrix, there's been loads and loads of work on how you can approximate these gram matrices, or maybe you can be clever into which kind of kernel matrix you choose, and you can sometimes reduce the cost for that. So I'm mainly going to be speaking about how you can do this first part. OK. As I mentioned, you can't do this in the case of intractable densities. So there's two options that we've really worked on. The first one, this was some previous work that Chris and Mark did, which was about how you can be really clever about your choice of kernel in order to always be able to compute this, even for posterior densities. And that's really what I'm going to be talking about for the rest of the talk, and we've really quite extended this methodology. And this is based on something called Stein's method, and I'll come back to that. And for this, I'll be needing to have some gradient information. So I'll need to be able to compute the gradient of the log density. Now, this is potentially, well, a little bit more than what you would need for standard MCMC, but also a lot of MCMC schemes, such as Hamiltonian Monte Carlo, actually use this gradient. And nowadays, we have a lot of software that can do automatic differentiation, so that's not necessarily a big problem. Another option which we've worked on is actually you can, as I did for my integrand for f, I provided a model of it with my kernel. I can do exactly the same. I can use a non-parametric model of pi, and then you can make things structurable this way. So here we've used a Dirichlet process mixture model to do this. Now, the problem with this is it's not very quick, but it also doesn't need gradient information. So now I'll focus on explaining this part. OK, so this little trick is actually related to something called Stein's method. And, well, I guess the easiest way to explain it is you're trying to look for a pair of operator and function space such that you can compute the integral of all of the functions to which you've applied the operator to analytically. So in this case, if I consider this operator, then I can compute, well, I can check that all the integrals of functions pi of sf, so I forgot to put the operator in here. So once I've applied the operator to f, I can compute all these integrals and they're all 0. And the way you can check that is by integration by parts. So if you do integration by parts of this thing, you can check that it's actually going to integrate to 0 if I assume something about what happens to the function on the boundary of the domain. So here there should be an S. And so this is where the gradient information comes in. OK. So what I could do is simply apply this operator to both components of my kernel. And I've added a +1 here. I'll explain why later. And so if I just expand what that is, it's just some combination of the kernel with the score and the gradient. So now I have a more complex kernel that I've obtained from a simple kernel. And I've added this +1 here because I want integrals of this kernel to be 1 or 0 for technical reasons. So now, if I go back to my original problem, which was that I need to compute these kernel means, well, actually, the integral of this kernel is just 1. I can compute that analytically using integration by parts. And therefore, I can compute my Bayesian quadrature weights analytically. And this is just going to be 1 times, a vector of 1s times the inverse of the Gram matrix. So now, something to note is that because this doesn't really depend on the normalizing constant of the density, I can actually use this with intractable densities. Okay, and I should say that this method with this type of kernel is what Chris and Mark called control functionals. So that's what I'm going to be referring to this method as. So in a recent work, we tried to develop some theory for these kind of special kernel spaces. So this is going to be some theory about how the root mean squared error decreases as n increases. So there's a bunch of assumptions. I'll come back to them. But first, I want to show you the rate that you get. So now the rate is n to the -1/2, which is what you get with standard Monte Carlo or MCMC, minus a min b over d plus epsilon. So the epsilon is just really small. You can ignore it. The a and b here are some assumptions that I'm making on how smooth the density and the kernel are. So if both the density and the kernel are very smooth, then I'm going to be getting a much faster convergence rate here. And unfortunately, the more high dimensional the problem is, the worse the convergence will be. Okay. So here, really, this is quite a significant improvement for certain applications which are low dimensional and very smooth, because I get a whole much bigger factor that decreases at the end. So to come back to the assumption, so I said I had this assumption about smoothness. I need to assume something about my choice of kernel and how it behaves on the boundary of the domain for the integration by part to work. And then the two things that these assumptions are perhaps quite strong, but they depend on some MCMC theory, which I'm not really an expert on. And so I'm sure these could be relaxed, but I don't really know how to do it. So the assumptions are that the domain is bounded. This is really to 5 minutes, OK. This is really to, OK, I can skip what happens to these assumptions. The only one to note is maybe this one, that I assume that my Markov chain from which I'm getting the points is uniformly ergodic, which is quite a strong assumption and doesn't hold for that many chains. So if I can just conclude with an example. So this is an example from it's a Bayesian inverse problem where I have a PDE with a set of boundary conditions, and it describes what happens with liquids on the ground, if you want. And this coefficient C here is how porous the ground is. And so what you're interested in is inferring how porous this ground is. So one thing that I can do, I can put a prior on this, and it's going to be a log normal prior that I've truncated at some point. So this is just a Fourier basis expansion. And what I'm going to do is I'm going to put a prior on the coefficients of this expansion, and I'm going to try to find their true value. So maybe the easiest thing to do is, so the integrals will be the posterior maybe mean of this and variance. So maybe it's easier to just see with a picture. So this is what I have. I have this domain. I have the boundary conditions on the sides, and I'm going to evaluate my function, well, my PDE on a grid. And so below is what a PDE solver tells me is the solution, and I'm going to try to find what those coefficients are in SC that I had earlier. So here, notice this parameter d, which is how long this series expansion is. And I'm going to look at the performance in different cases where I've taken d equal 1, d equal 2, d equal 3, etc. So in the first case, d equal 1. So I should say that I know what the true solution to this to these coefficients are because I've chosen them. So this is just to test how good the method works. So here I have what an MCMC chain would give me, and this is the root mean squared error as the number of points increases. So it slowly goes down. Whereas if I've re-weighted them using this control functional approach with these weights that I've obtained with this fancy kernel, then I can get a much faster convergence. However, this is only in d equals 1. And so when I increase, well, this is still good, but then it gets worse and worse, and you don't always get such an increase in performance. So it really depends on some problems. I should say here that, that was my next point, but here I've really been silly in the way I've chosen the parameters of my kernel. I've just fixed it at 1. I haven't done anything to learn that. I've also not done anything about the sampling of those points. So I've just reused the same points as here. Because actually, when you use these Bayesian quadrature or control functional estimators, the sampling that you might want to use may be quite different from what you would use with standard methods. And this is going to be my next point. So the stuff I'm currently working on is about trying to automate this method for practitioners. So for now, I guess if, let's say, a person that's trying to predict hurricanes' paths comes to me and asks me, can you solve me this integral? I need to ask him quite a few things in return. I want to ask which length scale do you want to use, what smoothness do you want to use, et cetera, et cetera. And that's not great. In practice, there's a lot of things that really matter for the performance of this method. One thing is how you sample the points. So one thing that we've been doing is optimizing the location of those points approximately, and that works pretty well in practice, but there's a lot of issues with this. And then another thing is how you learn the length scale parameters. So one thing you could do is put a hyperprior on them, but doing both simultaneously can be quite unstable and can actually result in really bad performance. So you really want something that somehow separates the way you sample the points and the kernel learning. And this is something that I'm currently working on, like building an adaptive SMC sampler to somehow target an optimal sampling distribution. And I think I'll conclude here. So I had a few other pictures to show you of preliminary results, but I think I will conclude here. So just in summary, so control functionals can be used to somehow post-process the output of MCMC chains and significantly improve on their performance in the cases where your problem is not too high dimensional and your target function is quite smooth. And that's potentially really useful for these kind of applications that I presented at the start. If I want to predict the path of hurricanes or do these integrals for rendering, this can actually really help because those are pretty low dimensional and quite smooth usually. Maybe some technical interesting questions would be, I've chosen this operator to which I apply to my kernel. There's a lot of other operators that I could use to do that. Would that actually impact the performance of the method? For example, I could add more derivative terms and do 2 integration by parts, but then I have a lot more information of pi. Does this actually improve? I don't know. This is something to look at. And yeah, I think I'll conclude here.